All right, so now we want to find a scalar potential of this vector field. Okay, so in other words, we have three equations that we want to solve. We want to find a function whose x derivative is equal to e to the power of x plus y, a function whose y derivative is equal to e to the power of x plus y plus z, and a function whose z derivative is equal to y. Now, let me just point out, there are many of you who are kind of good at just looking at these differential equations and figuring out what a solution should be. I'm not one of those people. I favor a more systematic approach, which is what I'm going to outline here, because it always works, among other things. So let's look at this equation here. And I'm going to color code these. I don't know how useful it'll be, but I have a lot of colors and I want to use them. So I have a function, I want to find a function. So I'm assuming that, so let me also say something subtle here, or make something clear that has been subtle. I'm assuming that there's a solution, and then I'm going to try to find that solution. If there's not a solution, there will be a contradiction, and we'll do an example where there's a contradiction. Okay, so I have a function. I know its x derivative is equal to e to the x plus y. Again, I'm assuming there's a solution. So I'm assuming there's a function whose x derivative is equal to e to the x plus y, whose y derivative is equal to this, and whose z derivative is equal to y. Okay, so this means that f of x, y, z is going to be equal to the antiderivative of e to the power of x plus y. But notice it's sort of like a partial antiderivative because we're only taking it with respect to x. Okay, but now, what is this? Well, the antiderivative of e to the x plus y with respect to x is e to the x plus y. But now let's think about what the constant of integration should be. The constant of integration needs to be some unknown function, which I'll call g, of y and z. Okay, because if the x derivative is equal to e to the x plus y, then any function of this form is going to have an x derivative equal to e to the x plus y, because the derivative of g of yz with respect to x is equal to 0. Okay, and now I want to use these other two pieces of information to figure out what g should be. So now I'm going to switch to green, and I'll work on this. Okay, so now I know that the y derivative of f is equal to e to the xy plus z. So whatever this f is, I know its y derivative is equal to e to the x plus y plus z. But this is equal to f. This is another expression for f. So the y derivative of this is e to the x plus y plus the partial derivative of g with respect to y of yz. Okay, and now look what happens. The e to the x plus y's cancel, and I'm told this gives me, not I'm told, but this gives me the partial derivative of g with respect to y is equal to z. Well, I didn't need to write this twice, but the partial derivative of g with respect to y is equal to z. So if the partial derivative of g with respect to y is equal to z, okay, then what do I know? I know that g of yz is equal to the partial antiderivative of z with respect to y, and this is equal to zy, and now the constant of integration is just going to be a function of z, which I'll call h of z. Okay, so g of yz is equal to zy plus a function of z. Again, because if you take the derivative of this with respect to y, the derivative of zy is equal to y, and the derivative of h of z with respect to y is equal to 0. And you'll get z, which is the derivative of g with respect to y. So g of yz is equal to zy plus h of z. And let me make this observation up here. At this point right here, notice that the e to the x plus y's cancel, and what we're left with is just a function of y and z. In this case, just a function of z. Okay, g is a function of y and z, so if all the x stuff didn't cancel, we would say that we would end up with the derivative of g with respect to y being equal to a function of x, y, and z, and that's a contradiction, and you'll see something like that in the next example. If you didn't follow all of that right now, just wait till the next example. Okay, and let me use, I think this is great. Okay, so h is still unknown. We need to know what h is. So we know the z derivative of f is equal to y. So the z derivative of f is equal to y. Okay, we know that another expression, so let me just make this a little more clear. This is now e to the x plus y. G is equal to zy plus h. So this is zy plus h of z. Okay, so the z derivative of f is equal to y. And now the z derivative of this function here is going to be y plus h of z. I'm just taking the z derivative of this function right here. Okay, this here is h of z. Okay, so this says y is equal to y plus h of z. H prime of z, because the derivative of h with respect to z is h prime of z. H is just a function of z, so it's just the ordinary derivative, not the partial derivative. So y equals y plus h prime of z. So this tells me that h of z is equal to a constant. In other words, well, really what it tells me originally is h prime of z is equal to 0, but this means h of z is equal to a constant. And so the final answer then, f of x, y, z is equal to e to the power of x plus y plus zy plus a constant. Okay, and again, the constant is like a constant of integration. Okay, so just to sort of recap what happened, we started by observing the fact that the derivative of f with respect to x is e to the x plus y. We took the antiderivative of that with respect to x and got e to the x plus y plus some unknown function of of y and z. And then we were able to use the other two equations, the y derivative and the z derivative, to figure out what g is. In the next example that we'll see, there will be a contradiction because in the next example, f does not have a potential.